These examples go with Lesson 1.5, Applications of Linear Equations and Modeling. Example 1. Use the point slope formula to find an equation of the line passing through the point -5, +2 and having a slope of -3. Then write your answer in slope-intercept form. Okay, the point slope formula is y minus y1 equals m times x minus x1. Now, the one subscripts are on here to remind us that they actually stand for numbers and actually a point that's going to be on our graph. And of course, m is going to be our slope. The x without a subscript will still remain an x and the y will remain a y. So once we've filled in our numbers down here, we're going to put this into y equals mx plus b form. All right, so the -5 we're going to treat as our x1. The +2 we're going to treat as our y1, and then the -3 we're going to put in for for m. Here's what we'll have. We'll have y minus 2 equal to -3 times x minus -5. Y minus 2 will be equal to -3 times, now here 2 negatives will make a positive, so we'll have x plus 5. Let's distribute the -3 into the parentheses. Y minus 2 is equal to -3x minus 15. And then to get y alone, we'll just add 2 to both sides. Y is equal to -3x minus 13. There we go, slope-intercept form. Example 2. Write an equation of the line passing through the points +2, -5, and +7, -3. First thing we're going to need to do is we're going to need to figure out what the slope of this line is, because I can't use my point slope formula without it. We'll treat this like x1. This is our y1. This will be our x2. And I'm going to move that negative down here. This will be my y2. y2 minus y1 divided by x2 minus x1. 2 negatives make a positive here. -3 plus 5, that's +2. And 7 minus 2 is 5. So our slope is going to be 2/5. Now, when we go to put it into our point slope formula, which looks like this, we have a choice. We can use either the x1, y1 point, or we can use the x2, y2 point. It doesn't matter, because when we put it back into slope-intercept form, we get the same equation anyway. They won't look the same initially. They won't be the same until we put them in y equals mx plus b form, which is what I'm going to do. So I'm going to choose the first point, +2, -5, just because the numbers are, well, I was going to say a little bit smaller, but they're not really. There's not really an advantage to using one over the other. So I'm just going to use the first one because it's first. All right, let's fill into our equation. So we'll have y minus -5 equals the slope we just found, 2/5, times x minus 2. Over here, 2 negatives make a positive. We have y plus 5 equals, and we can go ahead and distribute that 2/5 into the parentheses. We have 2/5 times x minus 4/5. To get y by itself, we're going to need to subtract 5 over here. So y is going to be equal to 2/5 times x. Now, -4/5 minus 5, this is -5 and 4/5, but let's put it in its improper form. Remember, 5 times 5 is 25, and 25 plus 4 more is going to give me 29 fifths. So there's our equation. Y is equal to 2 fifths x minus 29 fifths. Example 3. Write an equation of a line passing through the point -3, +2, and parallel to the line defined by x plus 3y is equal to 6. And then we're going to write our answer in slope-intercept form and in standard form. Okay, so we have our point here. We've got our x1, y1. What I don't have is the slope, but they did give me a clue here because they gave me the equation of a line and they told me that the two lines are parallel to each other. Well, parallel lines have the same slope, so if I know the slope of this line, x plus 3y equals 6, I'll know what slope I need to use that goes through the point -3, 2 to get the equation of my line. So I'm going to take the x plus 3y equals 6. I'm going to put it in y equals mx plus b form and find out what the slope of this line is. So I'll start off by subtracting x from both sides. That's going to give me 3y equal to -x plus 6. And then I'm going to divide everything by 3 so that I can see how my individual fractions are going to reduce. And I have y equal to, this is -1/3 times x, and then 6 divided by 3 reduces to 2. So the slope in this equation is going to be -1/3. And that's what I'm going to need to use to find the equation that goes through the point -3, +2. All right, let's put it into the point slope formula. So y minus y1 is equal to our slope times x minus x1. Let's clean this up a little bit. We have y minus 2 equal to -1/3. Over here, two negatives make a positive, so you have x plus 3. Y minus 2 is equal to, now we're going to distribute the -1/3 into the parentheses. -1/3 x. -1/3 times 3 is -3/3, and that just reduces to -1. And then to get y alone, we're going to add 2 to both sides. Y is equal to -1/3 times x plus 1. This is slope-intercept form. Now we're supposed to take this and put it into standard form. Okay, so there are 3 rules for standard form. Okay, rule 1, the coefficient on x needs to be positive. Ours is not. We'll have to fix that. The x's and y's need to be on the same side of the equals. Ours are not. We'll have to fix that. And rule number 3, no fractions allowed, and we have a fraction, so we're going to have to take care of that as well. I'm going to write my equation right here. This is in slope-intercept form. We're going to convert it over into its standard form. All right, let's get x and y on the same side of the equals. So I'm going to add this 1/3 x over here. I have 1/3 times x plus y equal to 1. All right, x and y are on the same side of the equals. The coefficient right here is a positive number, so I've got 2 of my rules taken care of. Now I just need to take care of the third rule, which is that no fractions are allowed. Well, to eliminate this fraction, and it's the only fraction in the problem, I'm going to need to multiply both sides times 3. 3 times 1/3, that's 3/3, but that just reduces to 1, so we have x. 3 times y is going to give me 3y. And over here, 3 times 1 is going to give me 3. And so here's my equation. This is in standard form. And that's it. Example 4. Write an equation of the line passing through the point -8, -4, and perpendicular to the line defined by 1/6x plus 3. Okay, so again, I'm going to try and write my equation in the form y equals mx plus b. And I know that I have my point here, x1 and y1. If I want to use my point slope formula, I need a slope. I don't have one. But they did give me the clue that this line is perpendicular to the line that goes through this point. Okay, my perpendicular slopes are negative reciprocals of 1. So we can think of this as a flip change. If I know the slope of 1, then I can flip it over or take its reciprocal and then change the sign on it. If it was positive, it becomes negative. If it was negative, it becomes positive. So what I would do is look at my equation here, put it in y equals mx plus b form. Well, that's done for me. So I can go ahead and pick up the slope. Now the slope of this line is 1/6. If I were writing the equation for a parallel line, I would use this slope, but I'm going to use a perpendicular slope. The perpendicular slope is going to take my fraction 1/6 and turn it upside down so it becomes 6/1, and it's going to change the sign. Since this one's positive, my perpendicular slope should be negative. Now your book is saying that to check your slopes and make sure you've got the right perpendicular slope, you would multiply these two together to see if you get -1. So let's see, -6/1 times positive 1/6, that's going to give me -6/6, which is -1. All right, so our perpendicular slope we're going to use is going to be -6. And this is the one I'm going to put into my point slope formula with the point that they gave me. All right, let's see what happens. We have y minus -4 equals our perpendicular slope times x minus -8. Let's clean this up a little bit. Two negatives here make a positive. That leaves me with y plus 4. Over here we have -6. Two negatives make a positive, so we have x plus 8. Let's distribute the -6 into the parentheses. Y plus 4 is going to be equal to -6x minus 48. And if I subtract 4 from both sides, we find that y is equal to -6x minus 52. And there it is in slope-intercept form. Example 5, a speeding ticket is $100 plus $5 for every 1 mile per hour over the speed limit. A, write a linear function to model the cost, S of x, in dollars, of a speeding ticket for a person caught driving X miles per hour over the speed limit. So A is asking us to write an equation. And we're going to put it in y equals mx plus b form. All right, the y, the S of x, this is going to be the cost of our speeding ticket. Okay. When you get stopped by a policeman in this town, you automatically have to pay $100 just for the privilege of being pulled over. So that's going to be back here. What's going to change is the $5. If you're only going 1 mile per hour over the speed limit, you pay $5 extra. If you're going 2 miles over, you pay $10 extra. 3 miles will be 15, and so on and so on and so on. So we have a variable cost right here for $5 times the number of miles per hour we're going over the speed limit. So it looks like our model right here, S of x, is equal to 5x plus 100. Now for part B, it says evaluate S of 15 and interpret the meaning in the context of this problem. Well, this is asking me to take 15 and plug it in for x into my model. So S of 15 is going to be 5 times 15 plus 100. Well, 5 times 15 is 75, and 75 plus 100 is going to give me 175. And so this means that someone going 15 miles per hour over the speed limit would pay $175 for their ticket. Then there we have it. Someone traveling 15 miles per hour over the speed limit would owe $175 on a speeding ticket. Example 6. At a summer art show, a vendor sells lemonade for $1.50 per cup. The cost to rent the booth is $120. Furthermore, the vendor knows the lemons, sugar, and cups collectively cost 40 cents per cup. A. Write a linear cost function to produce X cups of lemonade. Once again, we're going to try and put this in the form y is equal to mx plus b. Our cost function, c of x, all right, what it's going to cost us to actually make the lemonade. Well, it's going to cost us $120 to rent the booth. So that's automatically going to be here. It's not going to change. We're not paying $120 for every cup of lemonade we're selling. We're just paying $120 flat. It's our flat fee. I call this the one and done. We pay it once and we're done. Although the 40 cents down here, we're actually going to be paying that every time we make a cup of lemonade. So this one is going to be 0.40 times x. You can't really see that there. Let me redo this one. All right, so we pay 40 cents for each cup of lemonade and $120 to rent our booth. All right, there's our cost function. B, write a linear revenue function to produce X cups of lemonade. Now revenue, this is all the money that you bring in. So the revenue function, we're going to put it in this form right here. This is R. There is no flat fee on the revenue because we don't make, $50 just for showing up. We actually have to sell something, so there won't be any y-intercept on this one. And the money that we make $1.50 every time we sell a cup of lemonade. So $1.50 times however many cups of lemonade are sold, that's going to be our revenue function. C, write a linear profit function for producing and selling X cups of lemonade. All right, profit. This is what's left over after you have subtracted all of your costs from all of your revenue. So our profit function, P of X, is going to be our revenue minus our cost. And in this case, this is going to be 1.5x minus 0.40x plus 120. And if we distribute that negative into the parentheses, we're going to have 1.50x minus 0.40x minus 120, which is going to give me a cost function of 1.10x minus 120. That's our profit function. Now D is asking us how much profit will be made if 50 cups of lemonade are sold. In other words, what is P of 50? That's going to be 1.10 times 50 minus $120. And when I put this in my calculator, this gives me negative 65. Now, if we have a negative profit, that means we're losing money. So what's actually happened here is that we've actually spent more money in cost than we brought in by selling this lemonade here. So this is not a good thing. We lost $65 here. All right, E is asking how much profit will be made for producing and selling 128 cups. So now we're looking for P of 128. This is going to be 1.10 times 128 minus 120, and that's going to give me, when I put this in my calculator, this gives me 20.8, but we don't want to leave it this way because we're talking dollars and cents. So be sure you put that 0 on there for $20.80. So this is a positive number. So we actually made $20.80. And what this means is that the money that we were bringing in is actually more than the money we paid out to make this lemonade. That is ideal for a business. Okay, F is asking us to determine the break-even point. Now, the break-even point is going to be when your cost and your revenue are the same thing. So you don't make any money, you don't lose any money, so there's no profit there. Okay, we're going to figure out when our cost function is equal to our revenue function. And we're going to solve the equation. 0.40x plus 120 is equal to 1.5x. Let's subtract 0.40 from both sides. I have 120 equal to 1.1x. And when I divide by that 1.1, x is going to be equal to, and this is going to give me 109.0909090909, and so on and so on and so on. So if we round this, and this, the X, remember, stands for the cups of lemonade. If we sell 109 cups, we're going to have a loss, barely a loss. But if we sell 110 cups of lemonade, then we're going to have a profit in there. So we can't sell exactly the number of cups of lemonade to break even, but let's just say it's somewhere between 109 and 110. If we do one of those, we're going to come pretty close to breaking even and having zero profit. Example 7. Suppose that Y represents the average consumer spending on television services per year in dollars, and that X represents the number of years since 2004. Part A. We're going to use the data points positive 2, 308 and positive 6, 408 to write a linear equation relating Y to X. And we're just going to put this in Y equals mx plus b form. Okay, let's treat this one like x1, this one like y1, we'll treat this one like x2, this one like y2. We're going to need a slope first, so we'll find the slope, and then I'm going to use my point slope formula. All right, the slope will be y2 minus y1 divided by x2 minus x1. Well, 408 minus 308, that's going to be 100. And 6 minus 2 is 4. And this fraction reduces, and it will give me 25. And I think to write my equation, I'm going to use the first point here because the numbers are a little bit smaller than the other ones here. So to get the equation, or my model, we'll have y minus y1 equal to the slope we just found times x minus x1. Okay, let's distribute the 25 in the parentheses. We'll have y minus 308 equal to 25x minus 50. And then to get y all alone, we'll just add this 308 to both sides. And our model will be y is equal to 25x plus 258. B is asking us to interpret the slope in the context of this problem. The slope is 25, or 25 over 1. The Y values stand for consumer spending. and it's in dollars, okay? And then the X's stand for the number of years since 2004. So to interpret the slope, it's positive. So it looks like our spending is increasing. And how much it's increasing? Well, there's our number right there. It's increasing $25. Now, how often is it increasing $25? Every 1 year since 2004. All right, since we know that our spending is increasing $25 per year, we just write that out right here. The average consumer spending has been increasing $25 each year since 2004. C is asking to interpret the meaning of the y-intercept in the context of this problem. Now our y-intercept right here is 258. And remember, our y's stand for the average consumer spending on television services per year. Okay? And so the y-intercept would be the point 0 and 258. And X stands for the number of years since 2004. So if no years have passed since 2004, that means that in the year 2004, we would expect for consumers to be spending about $258 on their television services. We can say we would expect consumers to spend an average of $258 on TV services in 2004. And we really need to put in here about an average of, because not everybody's going to be spending $258. Some of them are going to be spending more than that. Some are going to be spending less than that. And if you think about that now with the cable bills, not everybody has the exact same cable bill every month because not everybody has the same plan. But they can get an average of what the average or what consumers are spending. Okay, part D. Use the model from part A to estimate the average consumer spending on television services for the year 2007. Well, remember, X stands for the number of years past 2004, so we are supposed to be finding what happens when X is equal to 3. And this is just going to be 2007 minus 2004. So I'm going to plug X equals 3 into my equation. Y is equal to 25X plus 258. So let's see what we get. Y is equal to 25 times 3 plus 258. And that's going to give me, when I put this in my calculator, it's going to give me $333. So we would expect the average consumer spending in the year 2007 to be about $333. And again, some will be spending more than that, and some will be spending less than that. Example 8. The data given represent the class averages for individual students based on the number of absences from class. A, we're going to find the equation of the least squares regression line. And then B, we're going to use the model from part A to approximate the average for a student who misses 6 classes. Okay, to do this, we're going to have to pull up Desmos. Okay, so I have Desmos pulled up here, and what I'm going to do is I'm going to take that table of information from the problem in example 8, and I'm going to enter it into a table over here in Desmos, and it's going to draw a scatter plot over here for me on the side. All right, so I have all my data entered into the table over here, and I told you it was going to immediately draw a scatter plot over here for me, but we can't see it. So if I zoom out some, I'm going to be able to see that. And there they are. There they are. These are the points right here from my table. And they look kind of like they're falling in a linear pattern here. So it's looking a whole lot like you've got a higher average if you've got fewer absences down here. In fact, the more absences you have on the x-axis, the lower it looks like your grade is going to be coming down here on the y-axis. Okay, now the part A asks us to find the equation for a least squares line, and what we're going to need to do is we're going to need to tell Desmos to do that for us. Okay, so to do that, we're going to put in y, and then instead of equals, we're going to put in the little squiggly line here, this tilde. This is an approximation, and we're going to put in mx plus b and it hasn't done anything for me because it doesn't know what to use. I need to tell it to use the table. So instead of just y, we're going to have to put in y1 and mx1, and that's going to tell it to use my table up there. And you'll notice all that stuff that just populated right there. This whole box right here. We've got an r squared, an r, our e1, and our parameters. This is what we're interested in, the parameters, because you'll notice it's m and it's b. M being my slope, b being my y-intercept, and I can plug them into y equals mx plus b, and I'll have my equation. So it looks like my equation is going to be negative 3.27 times x plus 98.15 if we round everything to 2 decimal places. And so that's going to be my model right here, negative 3.27x plus 98.15. And remember where we got them from. They came out of that box on the under the parameters. It gave me an m right here and a b. I just rounded them off to 2 decimal places where they were rounded to 4 before. Okay, part B is asking us to use our model, so our equation right here, and we're going to approximate the average for somebody who misses 6 classes. So what we're trying to do is plug in x equals 6. Well, y is going to be equal to negative 3.27 times 6 plus 98.15. And my calculator is giving me a 78.53. And if this student has a really kind professor, that grade will actually be rounded up to a 79. So we will expect somebody who misses 6 classes to get something around a 79, maybe a 78.